Hello and welcome to practice number 12 of Circuit Lab. We'll focus on LED, diodes, and operational amplifiers. My name is Mr. Burleson, and you may reach me at geaux15@hotmail.com. So, in the previous practice, we went over the types of switches, including single pole, single throws, single pole, double throws, double pole, single throws, and double pole, double throws as some of the more common types of switches. We also talked about fuses as a safety device to prevent overcurrent situations. We also talked about circuit breakers and how they don't burn out, but they actually trip, which is basically like a switch that automatically fails open when you have an overcurrent situation, and so they can be reset. We talk about how to solve for dependent sources and how dependent sources generally you have a voltage or a current source which is dependent on something else in the circuit, which can actually make the problem much more difficult to solve, but used quite a bit in amplifier problems. We talked about superposition and how you can use superposition when you have multiple independent sources. It does not work with dependent sources and it does not work with power, but you can take out individual dependent sources, or excuse me, you can take out individual independent sources and then solve your circuit multiple times and then add them up at the end. But let's talk about a diode. Now this is going to be for division C only. So a diode is a two-terminal, in other words, it's got an in and an out electronic component. Okay, it generally conducts current in one direction. So it's got asymmetric conductance. In other words, one way it acts very much like a short, and the other way the current tries to flow, it acts very much as an open. Okay, it has low, ideally zero resistance or a short in one direction, and high, ideally infinite or open resistance in the other direction. Okay, so if we talk about an ideal diode, it's a short when it's forward biased or closed or turned on. It is an open when reverse biased and open switch are turned off. Okay, now keep in mind real diodes have a very small resistance depending on their semiconductor material. And they also tend to have what is called a forward bias voltage. Okay, it's usually about 0.6 to 0.7 for silicon diodes. It's 0.25 to 0.3 for germanium diodes. Now, keep in mind some LEDs can be as high as like 4 volts. Okay, and if you look off to the right, this is a voltage versus current curve. And what you'll notice is that once we get above the forward bias voltage, pretty much it acts very much like a short. So that's the far right hand side that says forward. If you notice when it's in reverse bias condition, okay, virtually no current is getting through, so it's very much acting like an open. However, when we get really negative, we actually break down the PN junction of the diode, and we get into what they call avalanche conditions or breakdown conditions, where it again acts as a short because we've just basically overwhelmed the diode. You see the circuit diagram for the diode, which is just basically a triangle with a line on one end, and the line is where the cathode is, and then the part without the line is the anode. Okay, and so what you'll notice is that the current flows in the direction of the arrow. Okay, if it flows, it does not flow. One of my professors used to say when it tries to flow the other way, the straight line stops it. But of course, and then below you see what one actually looks like, and they'll always indicate which is the cathode. So an ideal diode has zero resistance in forward bias, and in reverse bias it has infinite resistance. So if I look at the example below, where I've got Vs that's driving that diode with a resistor, and then I've got an output which is basically my voltage across the resistor. Okay, you'll notice that when Vs gets above the forward bias voltage, okay, it very much looks like a short, as in the lower right hand side. However, when it is below the forward bias voltage, it very much looks like an open, so no current flows. Okay, and so like some of the current diagrams for an ideal diode is provided in the lower left hand side. You'll notice that basically the VI curve goes completely vertical at 0 volts. However, there's really going to be, it'll be slightly offset by the forward bias voltage. Okay, so if you look at in the lower right hand side, with the red line shows you an ideal diode, but like a real diode, it goes sort of similar, but it's offset by the forward bias voltage, which is about 0.7 volts for a silicon diode. Okay, and if you want to replace it in a circuit, what you do is that when it's forward biased, even though it's closed, you put in a 0.7 volt battery facing the other direction. And so then that way, what it does is that it shows the voltage drop across the diode. And if they give you the very small resistance that is in that real diode, you could also put that in there as well. But light emitting diodes are a special type of diode that emit a light when activated. The color is determined by the energy band gap of the semiconductor, which also affects the voltage drop. So I put a full table of all of this in the homework generator under the LED datasheet tab. Okay. Now, you can also find it on Wikipedia as well. Now, what they'll normally do is that when you have a light emitting diode, they'll either put a box that says LED with a direction, or they'll do the LED symbol with like pictures of the light emitting, as you see here. Also, make sure that you've got in your binder multiple copies of different cutouts of the different parts of a diode, of a LED. So, for a diode practice, okay, let's say this is our diode problem, okay? What we want to do is that we've got ideal diodes. So there's no forward bias voltage. The forward bias voltage is 0. There's no resistance in the diode. It's 0 as well. And so what ends up happening is that you don't know which ones of these diodes are turned on and which ones of these diodes are turned off. Okay? Now, what you have to do to solve it, is that you actually solve it for all 4 conditions. So it's much like a switch problem. So I solve it for D1 on and D2 on. You know, what if they're both on? And what you find out is that if they're both on, okay, the current can't go that way. So therefore, that one would not work. Okay, then I try for D1 off and D2 on. Okay, and what you find out is that that one also did not work. Okay, because what you'll notice is that I had plus 10 volts and plus 3 volts, so obviously D1 would have been on in that particular case. Okay, so we go down to what if they were both off? Okay, well, if they're both off, there's no current going through the 6 kilo ohm resistor, so therefore that's 0 volts. Okay, and then I'd have 3 volts and 10 volts, and so that didn't work. But what if D1 was on and D2 was off? And what you find out is that if D1 is on, okay, and D2 is off, then the voltage right above the 6 kilo ohm resistor is 6 volts. And the voltage, you know, on the other side of that other diode is 3 volts. And so that actually makes sense. That one made perfect sense. So, but you have to try all 4 different combinations and see which ones are valid. Okay, so it's much like this problem. Now, real diode problems using ideal diodes. So what you do with a real diode problem is that you replace those ideal diodes with you replace the real diodes with the ideal diode in series with your forward bias voltage, the opposite direction of the current, and a resistance. Okay, now keep in mind that RF is going to be really small, and we already know that the V on is anywhere from 0.6 for silicon to like 0.3, usually for germanium, or it might be 4 volts if it's an LED. Okay, but now let's switch gears and let's talk about an operational amplifier. Now, an operational amplifier, also referred to as an op amp, is basically a high gain voltage amplifier. It's a differential input, which means that it amplifies the difference. Okay, and it usually has a single-ended output. In other words, so if I look at the diagram on the right, there will be a plus and a minus input. Okay, and there will be an output. Now you'll notice that in pins 4 and 7, you've got V plus and V minus. And what those are is that's the power, if you will, for the operational amplifier. It's a very complex circuit, and you actually apply a high amount of voltage to power this amplifier, because it's got to get that extra juice from somewhere. Okay, and so if we were amplifying, let's say, an audio signal that might be very, very small, okay, but I put in a very large amount of V plus and V minus, then it can amplify quite a bit. Okay, this is very popular due to its versatility as a differential amplifier, and you can set it up easily as a comparator, inverting amplifier, or non-inverting amplifier. However, because we have all this complex circuitry, and because we have the power coming in from V plus and V minus, which normally is not even shown, you really can't do a KCL at the output of an op amp. Okay, so that's really important. It's the one place where we never ever do a KCL. So what does an ideal op amp look like? It's going to have infinite gain, which we know isn't possible. It's going to have infinite input resistance. So if I look at the inside guts, if you will, of the amplifier, okay, if I look at it, the difference between V plus and V minus is what we're going to call Vn. Okay, and what we're saying is that the G in this diagram would be infinite. Okay, well, given the fact that we use real circuits and Vs plus and Vs minus are not infinite, that's impossible. We're also going to say that Vn, the resistance that it faces under Rn, is infinite. It's not infinite, but it is ridiculously high. Okay? Then we're also going to say we're going to have an infinite output voltage range. So that means because we can do infinite gain, the output is infinite. We're also going to have what they call a common mode rejection ratio and a power supply reject ratio of infinite, which of course neither one of those are possible as either. Now, because Rn is infinite, that means that the voltage, okay, going into V plus and coming out of V minus is actually going to be 0. We're also that R out is going to be 0 because it's so well made, there's no internal resistance. There's going to be no noise, okay? And none of these are actually actual. So, but the two rules for an op amp that you should always remember is that if it's an ideal op amp, that V plus is equal to V minus, always. And the current going in to V plus and the current going in or coming out of V minus are also 0. You follow those two rules, you can solve any op amp problem. So let's talk about the three main uses of an op amp. The first one is a comparator. Okay, so if I have Vn, and that's my input voltage, okay, and if it is anything in this particular case, because the voltage at V minus, since there's no current coming out of there, is equal to ground, If it's anything, my V out is infinity. Okay? So if V plus is greater than V minus, it gives you the maximum output voltage. But now uh, if if V minus is less than V plus, then it gives them negative output voltage. So what it does is that uh, if you put in 0 volts, you get 0. But if it's a little higher, you get maximum positive, and if it's a little lower, you get negative. Now you'll notice that there is an error on here because the V minus and V plus actually should have just remained where they were, and I shouldn't have swapped them around. So this is called a comparator. Inverting amplifier is probably the most common amplification that I've seen. So basically what you do here is that you have an RN resistor and an RF resistor, and the ratio of those two resistors, okay, will determine what the gain is of this output. Because you'll notice that the V plus is driven to 0. I attached it to ground, and then so that means that V minus is equal to 0. So the current going through Rn is equal to Vn minus 0 over Rn. Okay, and since the current can't go into the negative side of the inverting amplifier, it has to go through the RF. So then the voltage there is equal to 0 minus V out over RF is equal to Vn over RF. Okay, so then I can figure out that the ratio between V out and Vn is equal to minus RF over Rn. So if I use a really big resistor for RF and a really small resistor for Rn, I can get a massive amount of gain. Or if they're very close, it'll be very close to just -1. Now, a non-inverting amplifier is where I take Vn and I put it into the positive side. And then on the negative side, what I do is I put in two resistors. I put an R1 and an R2 such that the R1 is grounded on one side, and on the other side, it's into the negative value of V, or the negative input of the operational amplifier. So the node between R1 and R2, its voltage would be exactly equal to Vn, because remember, the voltage at the nodes is forced to be the same. So therefore, the current going through R1 is equal to 0 minus Vn. And so that's the current. And since the current cannot come out of the negative side of the operational amplifier, it has to go through R2. So then, if I look at that current, it's the same current is equal to V out minus Vn. So V out minus Vn over R2 is equal to that same current. Using that, my gain comes out to 1 plus R2 over R1. So if I use a very large resistor on R2 and a very small resistor on R1, I can get a very large forward gain. So, what to do if it's a more complex operational amplifier circuit? Simplify the drawing to make it easier to see, or see if it's one of the common types. A lot of times what they'll do is they'll draw it up so it looks really complex, but it really is one of the common types. Simplify by combining resistors you have seen previously, by combining those in parallel, those in circuits, and repeating. In other words, you're always simplifying the circuit. Simplify the same circuits using KVLs and KCLs. However, remember, we never do a KCL at the terminal or at the output of an operational amplifier. Always use the golden rules of an op amp, but never ever do a KCL at the output of an operational amplifier. So if I look at this particular problem, now you'll notice they use the downward arrow, which is used quite often to indicate ground. Okay, so if I look at this problem really closely, okay, I can look at it and I go, wait a second, this looks very similar to some of the other ones I've seen. Okay, so I know that the input at the positive side of the operational amplifier is 0, so therefore the input at the negative side is also 0. Okay, now looking at the situation here, I can go, so now I know that this one in particular looks very, very similar to an inverting amplifier. Okay. And I go, so now I've just got to solve for all the resistance. And so if I know that Vs, the current going through Vs, is equal to Vs minus 0 over 1 kilo ohm. Okay? So I just solve for that current, and that's the same current going through the 5 kilo ohm resistor. Okay? So that same current goes through the 5 kilo ohm resistor, and then I can then take that 0, and then I can that's at the negative side or on the left hand side of the 5 kilo ohm resistor, and I know the current, so I can figure out what the voltage is between R2, R4, and R3. Okay, now that I know the voltage there, I then find out the leakage current that goes through the 1 kilo ohm resistor down to ground. Okay, and so now I know the current that goes through R4. And by knowing the current that goes through R4, I can then figure out exactly how much voltage I have lost through R4. And G should come out to negative 20. So, as you see, here is the details on how I solved that. So I solved it using nodal analysis at K, B, and C. You will notice I never do a KCL, if you will, at C. Never. So let's look at this one. Okay. Now this one, at first blush, you're like, oh my gosh, this is super complex. But in reality, okay, this one's actually sort of simple. Okay. Now, what's going to end up happening here is I'm going to look and I see the feedback for R3 and R4, and it just screams non-inverting amplifier. So if I take the voltage at the positive side of the operational amplifier and call that my Vin, if you will, it is straight up a non-inverting amplifier. And so then I've just got to solve for Vn. And Vn is a very simple, what we'll call it's a very simple voltage division problem. Okay, so now I use VA and VB, do the voltage division to determine Vn. So first thing I do is just looking at the op amp and the 20 kilo ohm and the 0.5 kilo ohm. That's obviously a non-inverting amplifier, and I ignore the rest of the circuit. That part I can solve real, and it's got a gain of 41. Wow, that's magnificent. Okay, now I notice that VA and VB is a simple voltage divider, okay, where I can figure out the Vn, or in this case V plus, is equal to 2VA plus B divided by 3. And that makes perfect sense, because if I look at it, VA in VB, you've got twice the resistance in VB as you do in VA. Okay? Then I combine them such that VO is equal to 41 times V plus, and that's where I get my 13.67 times 2VA plus VB. Again, as we've said before, when you argue in an illegal question, when you're in a competition, make sure you are doing it in a respectful way. You're very specific. Make sure you've reread both the question and the rules to make sure that you've identified a potential issue, and ask the question of how do you do it while following this one specific rule. Okay? Never, accuse them of being wrong or whatever. What you're really trying to do is saying, hey, look, I want to answer this question, but I want to do it within the rules. And a lot of times, the event supervisor's made a mistake, and then they'll say, well, answer it this way, or what have you, and then you just go forward. For your homework, all right, we're getting to the point where your binder should be in very good shape. I want you to do your circuit problems for level 15 diodes and level 16 operational amplifiers. Actually, I'm not sure the operational amplifiers one is completed just yet. I'd like you to also do these in-class practice problems on your own, showing all your work, making sure that your work can be followed by others. This is going to go into your binder so that you'll know how to do it. I want you to design an inverting amplifier with a gain of a negative 100 using 6 resistors and an ideal op amp. Okay, now think about that. I want you to use 6 resistors, and so what you're probably going to do is you're going to make you're going to design a circuit or a resistor network that gives you a particular resistance and on one side and a particular resistance on another side. Okay. I also want you to design a non-inverting amplifier with a gain of 3. Okay, and again using 5 resistors and an ideal op amp. Now you're probably thinking, holy smokes, he's always asking me to use a whole bunch of resistors. Yes, I am. And I want you to get used to that of designing a resistor network for a given resistance. And then I want you to put it into your non-inverting amplifier. And by the way, both of these designs are going to look a lot more complex, but when you break them down, they're going to look like just a standard inverting amplifier and a standard non-invert amplifier. Now I want you to design a circuit using diodes that will turn on a green LED, okay, when the input voltage Vn is greater than 3 volts. And I want you to assume forward bias voltages. Okay, so in other words, I want you to design a circuit such that when the voltage gets above 3 volts, the green LED turns on. When it's below that, it shouldn't turn on. Now I also want you to design a circuit using diodes that will only have positive voltage outputs. In other words, if it's ever a negative voltage, okay, if it's ever negative, you will have 0 output. Okay, now do not assume forward bias voltages, so I want you to use ideal diodes. Thank you so much and good luck.